Hello, welcome to Chapter 5, Section 5. We're going to be doing Example 3, and we're going to start to introduce the idea of complex numbers. So far, we've been talking about what the book and many teachers call, and many mathematicians call, imaginary numbers. And like I said, I'm going to keep throwing that out there, that I like to call them lateral numbers. And this is a new idea. Maybe you've come across it already, but in the sequence of learning, it doesn't come up in Algebra 1 and it doesn't come up in geometry. So if you had a previous teacher who has already mentioned this, then they just gave you like a little preview into the future. So in the sequencing, this is the first time that shows up. What have we done so far? Let's talk about that sequencing. When you were in kindergarten, first grade, and you were learning your numbers, you were learning how to count, you learned about 1, 2, 3, 4, 5, etc. And you learned about place value and some other stuff. Well, these are what we call the counting numbers, and some people call them the natural numbers. Then along the way, someone said, well, what about 0? Like, okay, how many stuffed animals does Alice have? She has 5. How many stuffed animals does Jim have? He has 17. How many stuffed animals does Tim have? He doesn't have any, so that's 0. Then we introduce negative numbers, and when we put the negatives, the opposites, I should say, of the numbers we were counting. So 1, 2, 3, now we got -1, -2, -3. Now we have integers. And throughout your career in math, we keep including new groups of numbers. After that, somewhere along the line, we talked about fractions, like 2/3, and negative fractions, like -1/3. These we call rational numbers. Then we ended up with numbers that we call irrational, and we get into that discussion. And in this example, square root of 2 is irrational. Pi is irrational. So now we put the rational and the irrational numbers together, and we call them real numbers. And previously, like for example, when we were studying when we first started studying the quadratic functions, one of the questions was, what's the domain? And we said the domain is all real numbers. Well, what do you mean by real numbers? People say that all the time, but are there numbers that aren't real? And the answer is yeah, but no. And that goes back to like the idea of, now we're going to introduce imaginary numbers. And again, I hate that we call them imaginary. I'm sorry, I'm going to keep saying it, but I hate that we call them imaginary. It makes me feel like we're talking about, like, imaginary history or imaginary animals or imaginary words or something. Okay. Imaginary numbers are numbers that happen. They're just not the numbers that we're used to. All right? And you probably ran into the same problem when you first introduced negative numbers. If we were to go back 3,000 years and talk to some of the Greek mathematicians and say, you have negative numbers, they would look at you funny, probably like the way you're looking at your screen right now. Or you look at me in class when I talk about this, because they didn't understand negative numbers. It wasn't until, I think, Al-Khwarizmi and some of the other mathematicians at that time. Anyway, let's get back to this. So you've got two sets of numbers. You've got numbers that we normally call real. That includes decimals, zeros in there. This is rational, this is irrational. We got positive and negatives, we got the whole thing. We got all the counting numbers. Then we have imaginary numbers, and they always have an I with them. This, I don't see an I, but that's I times the square root of 7 if I were to change it. All right? When I put these two together, I end up with complex numbers. Usually the question after I explain this, someone's going to ask, what's next after that? I don't know. This is as far as I think we've gotten. Maybe there might be something that we'll learn about later. I really think that the advantage of mathematics and science is not so much in this is what we know, but this is we're waiting to find out new stuff. So at this point, as far as like my graduate level math, this is as far as we've gotten. And if there's something after that, it'll be pretty exciting, let me tell you. So how do we actually represent a complex number? A complex number has two parts. And we usually write it like this: a plus b times I. This is the real part. This is the imaginary part. So the examples that I have here: 3 plus 7i, 3 plus 2/3 I, 4 plus -1 times I. I have a real part and an imaginary part. And the imaginary part can be multiplied by a number. Okay, but when I multiply, like 7 is a real number, but 7i is imaginary. That means 7 times the square root of -1, which is imaginary. So the 7 is not the important part. It's that you got 7 times I. 7 just tells me how many of them that I have. Now, I'm going to mention that video that I'm going to post again. They do a better job of explaining this, but we talk about the complex number plane. You're not going to have to worry about that now, but you will see this next year in pre-calculus, and it'll be a very important part if you go into more advanced math. So basically we have the real numbers and we have the imaginary numbers. All right? So if I said 3 plus 7i, I go 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. That's actually right there. And I drew it as a vector. We have not talked about vectors yet. If you watch the video, they'll explain a little bit more, but that's more advanced math than we've covered yet. You'll get into vectors in pre-calc. All right? So this is actually cool. This is, instead of like x, y, where both the axes are real, now we got real numbers going this way and imaginary numbers. This is why we call them lateral, because they're going in a different direction. They're going off that way. All right. Now, here's the thing about complex numbers. They have two, like I said, it's got two parts. So I have a plus bi. If I have another complex number written in a different way, so I have another number plus another number times I, these cannot be different. These cannot be different. There's no way of rewriting this so that these two are equal to each other. What that means is that whatever A is, it has to equal C. The real parts have to be the same. There can't be any combination. In other words, the plus sign just shows that I'm adding them together. It doesn't show any simplification at all. And the imaginary coefficients have to be the same. So it's more about what it can't do as opposed to what it can do. And again, this is just handing you off to pre-calc. So for the problems in this section that ask about this, I have this. I have a 3x subtract 5i, and that equals 6 subtract 10 times yi. They're just trying to find out what values of x and y are going to make this true. So the real parts have to be equal to each other. The 3x has to equal 6. So that means that the x has to be 2. So that's 3 times 2, which is 6. Both of them have to be 6. And the imaginary coefficients have to be equal. So -5 has to equal -10y, because both of them have a subtraction. And actually, I could have done this. I put the negative in there, but that's also 5 equals 10y. So I'm going to divide by -10, and I'm just going to turn around. Y has to be positive 1/2. So if I do 10 times 1/2, or 10 divided by 2, I get 5 here, and I get 5 here, and I'm subtracting, so -5. That's all you're doing with this. The real components, the real parts have to be equal, and the imaginary parts have to be equal. So what's the real part here? The real part is going to be 2x. What's the real part over here? The -8. 2x equals negative 8. Simple, x equals negative 4. The imaginary parts, negative 6 has to equal positive 20y. Well, that's not as easy, but I get y equals negative 6 over 20, which is going to reduce to 3/10. That's all there is to it. You're just setting the equal parts together, equal to each other. Sorry, excuse me, setting the real parts equal to each other and setting the imaginary parts equal to each other. And it looks confusing as heck. It's not. Here's the real part, here's the imaginary part. Here's the real part, here's the imaginary part with the negative in front of it. Okay? So, negative 8 equals 5x. These two are equal to each other. That tells me x equals negative 8 over 5. You can leave it as a fraction. Also, 6y equals negative square root of 6. So 6y right here multiplied by the I. What's being multiplied by the I over here? Negative, because of the negative sign, square root of 6. Now, you're probably thinking, well, how am I going to do this? All right? I'm going to divide by 6. And y equals negative square root of 6 over 6. That does not reduce. Okay? All right, we'll see you in the next video.